In this video, I'm going to show how to analyze polynomial functions of higher degree with an emphasis on the graphing characteristics. Before I go into the rules we'll be using, I want to review some definitions you should be familiar with. The first one is just what a polynomial looks like. This is the general form for writing a polynomial where the a values are the coefficients for each term and the x to the n. So if we're starting with like the fifth power, this is just showing how you would count down. Then you would have the fourth power, then you would have the third power because you're subtracting 2 from the first exponent all the way down until you get to the term that does not have an x at all. So the most important parts are that a is the coefficients and the x's are your variables with decreasing exponents. The leading term is one we're going to look at a lot in particular. That should always be the very first one if you have it in standard form. So the term that has the biggest exponent on the x's. And it is helpful to know that a polynomial of degree n, so if the biggest exponent is a 4, for example, then it will have one less of the extrema, so the maximums and minimums. So if it's the fourth power, then I know there's going to be one less, which would be 3 extrema. And it will have whatever the exponent is, that number for the zeros. So that's the most zeros it can have. So a fifth power polynomial can have at most 5 zeros. So now that we've reviewed some of the terms for a polynomial, here are some new rules we're going to be using. End behavior is a way of describing what is happening on the ends of the graph. Now when I refer to the ends, I'm referring to the left end and the right end, kind of like the bookends on a bookshelf. So we need to start off by identifying the leading term in the polynomial, the one that's denoted as a sub n x to the n power on the previous slide. And then we're going to focus on the exponent, which is the n value here, and the coefficient, which is the a value here. Now for the exponent, we're going to pay attention to whether it's an even or an odd number. And for the coefficient, we're going to pay attention to whether it's a positive or a negative number. By looking at those two rules, we're going to refer to this table to see what's happening on the far left and far right ends of the graph. When the function says the limit as x approaches negative infinity, that just means what's happening on the left side of the graph. And when it says what's happening when we have the limit as x approaches positive infinity, that means the far right side of the graph. So this table is saying on the left side of the graph, the y value is going to positive infinity, which means going up. On the right-hand side of the graph, the y value is going to positive infinity, which means it's going up. So when the coefficient is positive and the exponent is even, the graph goes up on the two outer ends of the graph. Here for the next situation, we have what if the coefficient was positive, but the exponent was odd? Well, then on the left side of the graph, it's going down to negative infinity. And on the right-hand side of the graph, it's going up to positive infinity. Now, if you look at the next row where we have a negative number for the coefficient, it's basically just flipping those values upside down. So on the left-hand side, it's not going up, it's going down. On the right-hand side, it's not going up, it's going down. And then the same thing for the odd exponent rule. Instead of going down on the left, it goes up on the left. And instead of going up on the right, it goes down on the right. So for now, just understand that the limit as x approaches negative infinity means the far left side of the graph. Just like if I said, where is x equal to negative 5? That's usually to the left of the origin. Negative infinity means infinitely to the left-hand side. And as x approaches positive infinity, that means on the far right-hand side of the graph, infinitely far to the right. So we use that to represent the right end. So here's the first example I'm going to break down. We have determined the end behavior of this polynomial. Now remember, for the end behavior, we're really just focusing on the very first term, the one with the biggest exponent on it. So I don't even care about everything else here to the right. We're just going to be focusing on the x cubed term. So if our leading term is 1x cubed, then we need to emphasize that the coefficient is a positive number, so I'm in this top row, and the exponent is an odd number, so I'm in this right-hand column. So my answers will be that on the left-hand side of the graph, it is going down, and on the right-hand side of the graph, it is going up. So the idea is right now, I know on the left end, the graph is pointing down. On the right side, it's going up. Now, we don't really know what's happening in the middle for the graph yet, so it could be all kinds of crazy shapes. We're going to be figuring that out more as we proceed through the lesson. Right now, the idea is just that we know on the left side, it's going down, and the right side, it's going up forever. Here's another quick example. Determine the end behavior of the given polynomial. We only want to focus on the leading term, so I'm going to be focusing on the negative 7 x to the fourth power for this one. So with a leading term of negative 7x to the fourth power, my coefficient is a negative number, so I'm on the bottom row, and my exponent is an even number, so I'm on the left-hand column. So my answer would be that the limit as x approaches negative infinity is negative infinity, and the limit as x approaches positive infinity is negative infinity. Graphically, that means it's going to be going down on both ends of the graph. So the positive and negative infinity values I was just showing are what we need to write for our answer, but for concept purposes, I want to continue to show that this means graphically the graph is going down on the two ends. And again, we don't quite know what's happening in the middle yet. We'll figure that out as we go along. Now here's one more example, but this time the polynomial isn't in standard form, it's actually in the factored form, which can be helpful for finding the zeros, but for identifying the leading term and the end behavior, we actually need to multiply this out. Now the good news is, if we only care about the end behavior, we don't have to distribute the entire set of factors together. We only care about the leading term, so we can really just focus on multiplying the first parts of each factor together, because that's what's going to give us our biggest exponent for the x values. So if I just do the 2x cubed times x, I'm going to end up with 2x to the fifth power. So I don't need to get the rest of the polynomial if all I'm doing is the end behavior. I now know what my leading term will be, and we can use this for finding the answer. So if you have a positive coefficient and an odd exponent, that's our positive and odd intersection here again. My answer is on the left-hand side, it should be going down to negative infinity, and on the right-hand side of the graph, it should be going up to positive infinity. So down on the left, up on the right again. So the ends of my graph would look something like this. So now we're going to start looking at the zeros and something called the multiplicity of each zero to identify what's happening more in the middle of the graphs, now that we've talked about the outside ends. Now, for the zeros and the multiplicity, we need the polynomials in factored form. So if you can use one of the more traditional factoring techniques like difference of squares or grouping or sum of cubes, that's great. But a lot of these are going to be bigger polynomials, and that's why we're going to use the process we've been covering in the previous videos on creating a list of possible zeros, testing them using synthetic division, and then switching to maybe the quadratic formula or factoring to find the rest of them. So we're going to have to factor these bigger polynomials using that more involved technique of creating the possible zeros and testing them. Then we're going to set each factor equal to 0 and solve for x. Those solutions we get for like x equals 5, x equals 7, x equals 9, whatever numbers we get, those are the zeros of the polynomial, which are also called the x-intercepts of the graph. So now we're going to know where our function touches the x-axis. And then the last piece is what we call the multiplicity. This is how many times each of the factors is repeated, and this will be noted in the polynomial according to what exponent we have on the factors. So if one of the factors has an exponent of 3, well then that solution has been repeated 3 times, and we say it has a multiplicity of 3 as a result. Now, the reason it helps us to talk about the multiplicity is because whenever you have an even number for the multiplicity, the graph is going to touch the x-axis at that point, but it's not going to cross the x-axis. If it was above, it's going to touch the x-axis and bounce off and stay above. If it was below and it comes up to touch the x-axis, it's going to bounce off and stay below the x-axis. And then the other situation is, what if you have an odd number multiplicity? So maybe the exponent on the factor is a 3 or a 5, or most commonly a 1. Whenever that happens, the graph will touch the x-axis and cross from either being below to above, or vice versa, from above to below. So here's the type of question you might see on the assignment when they're asking you to identify the multiplicity and how that affects the x-intercepts on the graph. Now, this one was already given in factored form. That's very helpful when this happens because it means we can jump straight into the step of setting each factor equal to 0 and solving for them separately. So this is what I get by solving the two factors, x plus 1 and 2x minus 3. I now know that the graph touches the x-axis where x equals negative 1 and where x equals 3/2. So we have the zeros, but the next part we need to identify is the multiplicity of each one. Now the multiplicity is just based on the exponents of those factors. If they don't write an exponent, that means it's a multiplicity of 1. If you do see an exponent, then that is the multiplicity of that particular solution. So here I've written in, based on those exponents, that the first solution had a multiplicity of 1, based on that factor having an exponent of 1, and the second factor had a multiplicity of 2, based on that factor having an exponent of 2. And whenever the multiplicity is an odd number, you will say that the graph crosses the x-axis at that x value, -1 in this case. And whenever you have an even number for the multiplicity, you'll say that the graph does not cross the x-axis at that x value. Now, sometimes the polynomial you are given will not be in factored form, in which case you may have to do the factoring on your own, which may also include the process of creating the list of possible zeros, testing them using synthetic division, and then switching to the quadratic formula after that to find the linear factorization on your own. So the first step is going to be breaking the polynomial down into that factored form. Now this polynomial could have been factored with the grouping technique, but I went ahead and showed the creating a list of possible zeros, testing with synthetic division, and then remember that if the solution that worked was +1, the factor is going to be x minus 1, so the sign flips on that number, and then the rest of the polynomial comes from this 1x squared plus 4x plus 3. I finished factoring that trinomial from there by looking for the two numbers that multiply to 3 and add up to 4. So here I've made my linear factorization. The next step is to set each factor equal to 0 to find the solutions, and then to identify the exponents on them for the multiplicities. So by solving for each factor individually, I've gotten the solutions of x equals 1, x equals -1, and x equals -3. But you'll notice that all three of those factors had the same exponent. None of them show an exponent, which means they all have an exponent of 1. So what that means is that for all three of those solutions, they have the same multiplicity of 1, and that means the graph will cross the x-axis at each of these x-intercepts. So now it's time to talk about how we can combine the x-intercepts, the multiplicities, and the end behavior to create the graphs for the polynomials that you're given. So you'll start off with the x-intercepts, plot them on the graph, then you'll use the leading term to find the end behavior and draw that on the graph from the ends of the x-intercepts. And then the last thing we'll do is we'll see where does the graph cross through the x-axis and pass to the other side, or where does it bounce off of it and stay on the same side. So here's an example where we are being asked to draw the graph of a polynomial, and this one is not in factored form. So our first step is going to be that we have to find the linear factorization on our own. So here you can see I found the first 0 by using synthetic division with +1, and then I did synthetic division again. Since this is the next to the fourth polynomial, I had to find a second number using synthetic division, but I used the same number again. You can have the same number used multiple times for the factorization. That is in fact what a multiplicity is. So +1 worked a second time, which means I now have two factors. I have x minus 1 and x minus 1, which I'll go on to eventually write as x minus 1 squared. And then I finished factoring this piece in here, the x squared plus 2x plus 1. So I had to find the two numbers that multiplied together to equal c, but added up to equal b, the middle value. And in this case, that was +1 times +1, while adding 1 plus 1 equals 2. But this is again another example of multiplicity. I have the same factor twice, so instead of writing that out twice, we write it one time and we put a second power on it. So with the linear factorization done, we can identify that there is a solution at +1 from this factor and -1 from this factor. So those are two of my x-intercepts on the graph. For the end behavior, we look at the leading term. I have a positive coefficient and an even exponent, so you should see that on the left-hand side it's going up to +infinity, and on the right-hand side it is going up to +infinity. So now I'm going to apply that on the graph starting from my x-intercepts. So the left-hand side is going up to +infinity, and the right-hand side is going up to +infinity. So now we just need to figure out what's happening in between the dots by using the multiplicities on our exponents. We said for the solution at +1 and at -1, they both had an even multiplicity, which means when the graph touches the x-axis, it does not pass through to the opposite side. It instead stays either above or below. So the graph bounced off at -1, and in fact it bounced off at +1. So this graph would stay above the x-axis on the entirety of it. It just touches at these two locations. And for the last example, I've already gone ahead and worked out the factoring here so that we can just focus on the part for this video. Once you get down to your zeros, I drew those dots at -4, -1, and +1, because remember we have to set those equal to 0 and solve them. Now these all had a multiplicity of 1, so I'm expecting the graph to cross through the x-axis at each of these points. We start off with the end behavior. Since our leading term has a positive coefficient and an odd exponent, it should be down on the left, up on the right. So I can now apply that to the farthest left endpoint and the farthest right endpoint on my graph. And then at each of the solutions, at each of the zeros here, the graph is going to touch the x-axis and then keep going through to the opposite side. And then -1 had an odd multiplicity, so it's going to touch the x-axis and keep going through to the other side. And then it's going to come back to the next dot on the graph and touch it and continue through to the other side. So this would be a rough idea of what the polynomial would look like, although to find precision for like exactly how high it goes above and below when it crosses from one side to the other, we would really have to plug in numbers like x equals 0 to find exactly where it hits for the y coordinate. But that's it for drawing the graph of a higher polynomial.